Hi, hello, good afternoon, one and all. Welcome to the session. Can you confirm about audio and video? If anybody is there, please do let me know about audio and video so that we can move ahead. Hi, Yogananda, how are you? Please do let me know. Please do let me know if everything clear. Then we'll move on to the session. Is everything clear? Done. Everything clear. Hi, good afternoon, Shiva. Right. So here in this session, I'm going to discuss about some formulas, especially the electrical part, electrical measurements part, electronics measurement part, and or otherwise instrumentation part will be discussed by Surendra sir. And I'll be taking electrical part. So from right from PMMC instrument to the CRO or otherwise up to energy meter bridges, I'll try to cover the formulas and simple questions I have got here. I've got around 20 plus questions with me, and I'll give you some formulas also, important formulas, so that it will definitely help you to crack the examination. Hope so. Okay, so let's move on. Let's move on to the session. Are you ready, guys? Are you ready, guys? All right. So before moving on to the session, there's a small introduction about myself. My name is Naveen Gollapally. I have 7+ years of experience in teaching. Most of the times I'll be teaching networks, measurements, machines, and power system. Right. So these are my interested areas. And right, let's move on to the session very quickly so that we'll finish it very quickly. Okay. So the first meter I'm going to take up in this session is going to be PMMC instrument. Okay. So I don't think if you take up A4 size paper, I think back to back, that means what, front and back, that paper is enough. I'm damn sure that one paper is enough to put all those formulas in one paper. I'm speaking about electrical measurement part. So let's have a look at that formulas. Come on. So here is my PMMC, permanent magnet moving coil instrument. So the formulas you need to remember, the formulas you need to remember is about deflection torque and of course control torque, and at steady state condition how will be the deflection torque and control torque, and similarly the range extension formulas, that is if you want to convert the PMMC meter into PMMC ammeter or to increase the range of an ammeter, what kind of resistance you have to place. Similarly, if you want to increase the range of an voltmeter to a large value, what amount of voltage, what amount of resistance you have to place in series with the meter. So those things you need to remember. So I'm listing out them, the important formulas. The first formula I can take out, it is deflection torque. Deflection torque will be B into I into A into N. B is the flux density in Tesla or otherwise Webers per meter square. I is the current flowing through the current coil. A is the area of cross section of the coil, and N is the number of turns. So this is your Newton meters. And TC, if it is spring control, you can simply take it as Kc into theta. Kc is the spring constant. All right. And if it is gravity control, generally in PMMC instrument we do not use, we do not go for gravity control. Spring control is enough. I'm writing, but still separately I'm writing. This is kg into sine theta. So remember, in most of the PMMC instrument, we'll go ahead with the that is spring control torque, not with the gravity control torque. In general, MI instruments, especially the panel board meters, those who are which are going to be placed in vertical manner, so that can employ gravity control technique. All right, now at steady state, Tc equals to Td. All right, so damping torque is going to be 0. The damping which we are going to prefer in PMMC is going to be eddy current damping. Deflection, control, and damping is going to be eddy current damping. Yes or no? So at steady state, Tc and Td are equal and opposite, and damping will be 0. Now if you equate this, I am taking spring control, so I am going to get a formula as theta is equals to B into I into A into N divided by Kc. Maybe radians or otherwise degrees you can take up, no issues. So this is one more formula you need to remember. From this I can say, if PMMC meter is designed, flux density, area of cross section of the coil, number of turns, spring constant, if these are constant once the meter is designed, now you can expect theta is directly proportional to I. So this is one more important formula. Doesn't mean that this is the point you need to remember. Theta is directly proportional to I, or theta is directly proportional to V also you can write. Okay, so these are the formulas related to the steady state condition, or otherwise deflection torque, control torque, and damping torque. All right, and the other formula you need to remember is, if you want to increase the range of a PMMC instrument to measure large values of current, you need to place a shunt, and this shunt value is of Rm by M minus 1. M is, what is M? Capital I by Im. So this is extended current, and this is the meter current. Okay, now similarly, if you want to increase the range of a voltmeter, you need to place a multiplier, and this will be around Rm into M minus 1, where M is extended voltage by meter voltage. Okay, so these formulas you need to remember. Sometimes I'll ask you with which material the shunt is going to be designed, what is the value of the shunt, what is the value of the multiplier, like that they are going to ask you. Can you tell me what is the value, what is the range of shunt? Can you tell me what is the range of the shunt? So shunt value is going to be in the less than 1 ohm range, and series value is going to be greater than, it's going to be around in the range of kilo ohms and mega ohms. You can take up kilo ohms, that is fine. So these generally manufactured with copper plus manganese. So we call them as swamping resistance. So these are the formulas you need to remember when it comes to PMMC instrument. Okay, so let's have a look at the questions based on the formula. Let's move on. So I have got a question here. All right. A moving coil instrument has the following data. The number of turns he has given, the width of the coil, depth of the coil he has given, flux density also he has given. If the control spring is 2 micronewton meter per radian, or 2 micronewton meter per degree he has given, then the deflection of the pointer when the coil carries a current of 10 milliamperes is. Come on, my dear. So try to solve and tell me the answer. Anu, I have the question at the end. Not so many questions. Actually, even I forgot about to take up the formulas on networks also. I took only like questions, only the areas I have covered. Okay, this time I have got some formulas and I have got some questions. So let me go through that. If we find some time, then we can move on to the questions also. Right. Can you tell me what is the value here? Is asking the deflection of the pointer. Theta is asking. Theta. So theta is equal to, just now we have seen, B into I into A into N divided by Kc. All right. So what is B? B is of zero point 0.1 Tesla into I is of 10 milli. 10 milli whole 10 milli, yeah, 10 into 10 to the power of minus 3 into area of cross section. Area of cross section 20 into 30 into 10 to the power of minus 3 into 10 to the power of minus 3. So I am writing it as 10 to the power of minus 6. Now number of turns are 100. So divide with the spring constant. What is the spring constant? 2 micronewton meters per degree. So 2 into 10 to the power of minus 6. So if I cancel, of course, this denominator 10 to the power of minus 6 and 10 to the power of minus 6 gets cancelled. Of course, this even 2 also we can cancel out, and this 0.1 into 10 will be 1. So rest we left out with 3, and this is 10 to the power of minus 3 and 3 zeros. So 30 degrees. I am getting theta equal to 30 degrees. Is it so, everybody? But he has given the answer in terms of radians. So it can be 5 by 6 or not. 30 or 60. How much this one? I am getting 30. Everybody getting 30 or 60? Okay. So 5 by 6 radians. Everybody has got the answer? Respond, my dear. Everybody got the answer or not? Right. Done. Now look into this one. So that is the question based on theta, that is at and a steady state condition. Now there is one more question I have got here. A 1 milliampere meter movement with an internal resistance of 100 ohms is to be converted into 0 to 100 milliamperes. The value of shunt resistance required is. So just now I said RSH is equals to Rm by M minus 1. Rm is a meter resistance, that is 100. M. What is the multiplication factor? M. M is in the extended value, that means what? To what value of current you want to extend? So that is I. So I wanted to extend up to, I'm so sorry. I wanted to extend up to 100 milliamperes. So 100 milli divided by meter current is 1 milli. So you can cancel out, so you'll get 100. 100 minus 1 is going to be 99. So 100 by 99, definitely it is going to be greater than 1. Definitely it should be greater than 1. So probably you might be getting it as not 1.09. 1.1 is also not fine. 1.01 probably. Is this the answer you are going to get? Is this the answer everybody has got? So remember, be careful. So it is a 100 divided by 99. So definitely answer should be greater than 1. Right? 99 ones 99. So only 1 remains. So take up 2 zeros again. So 0.01 you are going to get. Now can you answer this question? A milliammeter of 1.5 ohms resistance rates up to 100 milliamperes. Okay. The series resistance required to make it as voltmeter reading up to 100 volts. So he's asking RSC. Rm into M minus 1. Rm I have got it as 1.5. M, I have to calculate M. M is a multiplication factor, external voltage by meter voltage. At what value I wanted to, we have to extend 100 volts. Right. Now meter voltage is how much? We do not know. But meter voltage you can calculate like this. He has given meter resistance and he has given full scale current of meter also, that is 100 milli. So meter current into meter resistance, you are going to get obviously meter voltage. So that is 100 milli into 1.5. So if I take up 100 gets cancelled. Milli, if milli goes up, it will be okay 1000. So 1000 divided by 1.5. Is it so? Thousand divided by 1, or otherwise let me write this one. Yeah. 1000 divided by 1.5, right? Okay, anything is okay, fine. 1000 divided by 1.5 minus 1. So definitely pen is not good, it seems. Definitely, and this 1000 divided by 1.5 will not be greater than 1000. It will be less than 1000 only. Less than 1000 minus 1. So almost you are going to get near to 1000. So that value into 1.5. So can you tell me what is this? So 1.5 gets cancelled. So 1000 minus 1.5. How much? 1000 minus 1.5. No? 1000 minus 1.5. So 998.5. Are you going to get C value? Very good. Superb. Hassan and Yogananda done. All right. So this is one question on RSC, one question on RSH, and one question on deflection torque. There are sometimes other kind of questions also you can expect, like this one, that is loading effect based on sensitivity. Based on sensitivity. So this is very important formula. Sensitivity is inversely proportional to current. Sensitivity units are ohm per volt. Okay, so we write from the sensitivity you can calculate the voltmeter resistance, that is sensitivity into voltage, VFSD, full scale value of the voltmeter. Remember, this is also one more formula, one more important formula you need to remember. Is asking the loading effect in voltmeter can be avoided by. How do you avoid the loading effect? Will you use high range of voltmeter? Will you use high sensitivity of voltmeter? High sensitive voltmeter? Will you use accurate and precise instrument? Will you use low sensitive voltmeter? What could be the answer? Loading effect. Loading effect means when you have a circuit, and in that circuit if you connect a meter to measure some quantity, maybe voltage, maybe current, let it be anything. When you introduce a meter resistance is going to be introduced into the circuit, and therefore the circuit resistance is going to be altered. So that kind of change in resistance, you can call it as loading effects. So that can be minimized. That can be minimized only when the meter resistance is very high. Only when the meter resistance is very high. Especially see here, I have R1, I have R2. Now if I wanted to measure the voltage across this R2, this voltmeter resistance should be very large. I am speaking about voltmeter. If it is ammeter, now you have to please, obviously the ammeter resistance is very small. This voltmeter resistance should be very large, then only this change in resistance is going to be very small. So high resistance is absolutely highly sensitive meter, no doubt at all. Loading effect in the voltmeter can be avoided by using high sensitive voltmeters. Is that clear? Very good, Hassan. Okay, so this is very important question. One important question you can expect. Maybe may not be only this way. They might be asking the question on formula also. So these are the 2-3 different types of models on PMMC instrument. If not on formulas, you can expect the question on what is the material used to design the springs, what is the material used to design the permanent magnets, or what is the material used to design the pointer. That kind of questions they'll ask. Otherwise they'll ask you what is the purpose of iron core between the permanent magnets in the PMMC instrument, what is the purpose of aluminum former. That kind of questions in theoretical questions also you can expect, but try to have basic idea about the each and every element or each and every part in the meters. So that is my sincere request. And sometimes I'll ask you about the scales also. Theta directly proportional to I, so linear scales. Theta directly proportional to I square of the current, non-linear scales. Okay, so that kind of questions also you can expect. Hi, Bhavani, how are you? I'm fine. And so let's move on to the MI instrument. Let's move on to the MI instrument here. So moving iron instrument. So again, I'm representing the formulas. The deflection torque is going to be half into square of the current into dl by d theta, Newton meters. And the control torque will be, if it is a spring control, kc into theta. If it is a gravity control, kg into sine theta. So remember that. So those are not going to be changed. So right. So TC is here. Now at steady state, I am writing at steady state TC equal to TD. Therefore, I can write here Kc into theta. If you substitute here, half into square of the current divided by Kc into dl by d theta. Sometimes I'll mention dl by d theta as constant. Sometimes I'll give you the inductance value also. So please remember these formulas. Okay. So from this one I can write theta directly proportional to square of the current. So here non-linear scales you can write. Non-linear scales. Cramped scales or non-uniform scales. Now at the PMMC, I forgot to write here. Here this is going to be linear scales. Okay. So these are the formulas, the important formulas you need to remember. Another formula you need to remember is coming to the range extension. To say exactly, it is not going to be for range extension. Keeping the shunt and keeping the multiplier in MI instrument is not going to be, the primary intention is not to increase the range of the MI instrument. It is actually to compensate the frequency errors, okay, in the MI instruments. Okay, so the shunt time constant to eliminate the frequency, errors, we use shunt in the ammeter. That shunt time constant must be equals to meter time constant. In another way, we write it as LSH by RSH is equal to LM by RM. Alright, so this is the thing. And the shunt resistance, the value of shunt resistance is equals to again same as the PMMC instrument, that is RM by M minus 1. So this is the point you need to remember. Coming to the voltmeter, the voltmeter, in order to eliminate the frequency errors, we are going to take the help of capacitor. So in the voltmeter, we will place a capacitor, and the capacitor value is practically it is 0.41 times Lm by RSC square, and on an average or roughly you can take it as, I'm so sorry, this pen is not supporting, maybe some problem, or else you can take up it as theoretically Lm by RSC square. I missed square term here, I'm so sorry. Okay, so these are the formulas you need to remember when it comes to MI instrument. Okay, all right, so let's move on. Very good, Hassan. Let's move on to the problems based on this one. Okay. Now here is, I have got one question. The inductance of a moving iron instrument is given by L is equals to 10 plus 5 theta minus theta square microhenries, where theta is the deflection in radians from zero position. The spring constant 12 micronewton meter per radian. The deflection of the pointer for a current of 5 amperes is asking. He has given current, he has given spring constant, he has given inductance also. Now you simply substitute in the equation. So theta is equals to half into I square. I square is 5 square. So 5 square will be 25 divided by Kc. What is Kc? Kc is 12 micro. Into differentiation of inductance. Differentiation of 10 is 0. Differentiation of 5 theta is 5. And differentiation of theta square is minus 2 theta micro. So do not miss this micro. So micro gets cancelled. Now this will be 12 2s are 24, and numerator I have got 25. I am just cross multiplying here. So 24 theta is equals to 25 into 5 minus 2 theta. 5 minus 2 theta. Twenty-five 5 is 125 and 25 2 is 50. So if this 50 comes onto the left side, it will be 74. So theta is equals to 25 phi is 125 divided by 74. So obviously this is 150. If I have got the numerator as 150, 75 2 is a 150. So the answer should be less than 1 only. The answer should be less than 1. So you select, and of course he has given the units as Newton meter per radian. Alright, so obviously you'll get theta in radians. The answer should be less than 2. The answer should be less than 2 radians. So this is not going to be the answer. So obviously this might be the answer. But another two options are given in degrees. Another two options are given in degrees. So you have to check this one. So you have to do some small mathematical calculations. So it might be resulting 1.68 Newton, 1.68 radians. So if that is not matching, then convert into degrees. You will get any one option, maybe B or D. The option is answer is 1.68 degrees here. Very good. Yogananda, superb. Now I have one more question. Please try to answer this question properly. I have like this question is like this. Which of the following statements is wrong? Which of the following statement is wrong with respect to the MI instrument? MI instrument scale is not uniform. Yes, this is true. Theta directly proportional to square of the current. So it is true. This is true statement. B. For low voltage range, the power consumption is more. For low voltage range, the power consumption is more. Let me show you here. The MI instrument is going to be like this. RM, RM, LM. And if you want me to show the this one also series resistance and capacitor, if you want me to show, like I can show here also. So I am going for some range value, some range of voltmeter. Now what he is saying is, for low voltage range, the power consumption is more, he is saying. If you want to measure large voltage, definitely you have to connect across the large voltage only, no? Right. So if the supply voltage if the voltage applied across the meter is low, the current flowing through the meter is also low. If the voltage applied across the meter is high, current flowing through the meter is also high, because this impedance is going to be constant, right? The impedance of the meter is going to be constant. If the meter is placed across a large voltage, large current will flow. If the meter is placed across a low voltage, low current will flow. So obviously, if the voltage is low, he's saying that for low voltage range, if the voltage is low, obviously current is also low. Now, low voltage, low current, this will lead to low power, not a large power. So this is absolutely a false statement. Option B is a false statement. Did you understand? You know, at any point of time, if you do not understand, please comment in the chat box. So as I'm getting, you know, as the comments are going to be delayed by some time duration, meanwhile I'll be proceeding to the next comment, the next option. Repulsion type instruments are much more common than attraction type instruments. Yes, it is true. It is absolutely true. Do you know why? Do you know why? If you see the construction, you will get an idea. Attraction type instrument, there will be an electromagnet. There will be an electromagnet. And near to the electromagnet, we should place a moving iron disc. So if the moving iron disc, if you place a moving iron disc here at this point, the inductance air gap is different. If air gap is different, inductance is going to be different. If you place a moving iron point here, it will be again inductance is going to be different. Designing attraction type instrument is very, very difficult compared to repulsion type instrument. So repulsion type instruments are much familiar, much easy to design rather than attraction type instruments. So the designing constraint is a design constraint. Placing the iron piece is a very, very difficult task out there. Attraction type instrument will usually have more inductance than that of corresponding repulsion type instruments. So that is what I said just now. The inductance of the coil is going to be dependent upon definitely the placement of the iron piece also. Okay, so here is the more influencing thing I can say. So out of 4, only one is going to be the false answer, false one. That is, for low voltage range, power consumption will be low only, but not more. Now here, look into this one. The deflection of the pointer of an ideal moving iron ammeter is 30 degrees for 2 amperes DC current. If a current of 4 sin 314t amperes is passed through ammeter, then the deflection angle is. So it is a moving iron instrument, moving iron ammeter. So through the moving iron ammeter, we are sending 2 amperes DC current, and we are sending 4 sin 314t AC current. Okay, all right. So that means what it is like, we are connecting an MI instrument like this, a DC source. Okay, so DC current and AC current both are there. So MI instrument is going to indicate RMS value of the quantities which are going to be applied. Yes, sir. RMS quantities which are going to be applied. He is not asking what is the indication. He is asking what is the deflection angle, theta. So theta is directly proportional to square of the current. So theta 2 divided by theta 1 is equals to I2 divided by I1 whole square. I'm so sorry about this one. This is I2 by I1 whole square. Now can you substitute the values? Theta 2 is equals to I2 is 4. So that is, this is the maximum value of the AC current, but I want RMS current now. So 4 by root 2. I'm so sorry. This is disturbing a lot. Please do it and tell me the answer. Can you tell me the answer? 4 by root 2 whole square by, and I1 is of 2 amperes. That is 2 whole square into theta 1. Theta 1 is of 30 degrees. So 4 by root 2 is 16 by 2. 16 by 2 is 8. 8 by 4 is 2. So 2 into 30 will be 60 degrees. Are you getting 60 degrees? Everybody getting 60 degrees? Is it 90 degrees? Hassan? I am getting 60 degrees. Is it so? Come on, my dear. Let's move on to the next question. All right. Here is, I have got one more question. The value of capacitance connected across a series resistance of 5000 ohms with a coil inductance of 1 Henry and a moving iron voltmeter. 1 Henry of a moving iron voltmeter. That is a better, and not and. To eliminate the frequency error is around. The value of capacitance is asking. C is equals to. Check with the 0.41 times Lm by RSC square and check with the Lm by RSC square. Sometimes they'll give you two answers. Sometimes very rarely they'll give you. The answer may be with any one of the formula. So that is the reason why check with 0.41 times Lm by RSC square and check with Lm by RSC square. So Lm is 1 Henry, RSC is 5000 whole square. Lm by RSC square, na this one. So 5 square is 25 and this 1000 square is mega, of course. So 10 to the power of 6 divided by 25. So what is 25? 1 by 25 is going to be 0.04 probably. 0.04 mega. So sorry, not mega, it is 10 to the power of minus 6 now. Micro. So you'll be getting probably it as 40 millifarads. Is this the answer? C I am getting. I am getting C. Are you getting C or some other value? You try with 0.41 times also. 0.41 times 40. That's it now. 0.41 times 40. So 0.41 means zero point 0.4 into 40. It could be around 16 millifarads. So there is no option which is matching near to 16 milliampere, 16 millifarads. All right. So these are some questions on the formulas and the models I have given here. Okay. And there is another thing you need to remember is there is one beautiful question. Actually, I did not take up that one. Remember, moving iron instruments are going to indicate low value for ascending currents. If the current is increasing, the moving iron instrument will not indicate the same value. I'll tell you. Please remember this one. I'll write here. Please make a note of this one. This is very good question. MI instrument, MI meters reads low values for ascending currents or for ascending quantities. Similarly, MI instrument reads high value for descending quantities. That means what? When you are increasing the current from 1 to 2, 2 to 3, 3 to 4, and so on. When you are increasing the current from 1 to 2, it will not measure 2 amperes. It will measure 1.8. 2 to 4, it will not measure 4. It will give you 3.8. 4 to 10, it will give you 9.8, like that. Now, when you are decreasing the current from 10 amperes to 8 amperes, 8 amperes to 7 amperes, 7 amperes to 5 amperes, and so on. When you move from 10 amperes to 8, it will not indicate 7.8, it will indicate 8.1, 8.2. When you decrease the current from 8 amperes to 5 amperes, it will not indicate 4.9, it will indicate more than 5, that is 5.1 or 5.2. Because the induced EMF across the coil is a main reason to give the deviations in the measurement. Okay, so this point you remember. Similarly, I am writing here. Similarly, high values for descending quantities. All right. So this point you need to remember. Now, I've got AV method and VA method. So that is all about PMMC and MI instrument. Now, if you wanted to measure the power, we have got DC power and AC power. So you can take up AV, ammeter voltmeter method, and voltmeter ammeter method. Okay. So the points you need to remember in AV method and VA method is like this. AV method is useful for low resistive loads. VA method is useful for high resistive loads. Okay. So why? Because if you use on low resistive load, error will be less. Here in this error measurement, here also PM is greater than PT, that is PT plus error. The error is due to voltmeter, load side instrument, that is VL square by RA. AV method is same like LC short, and here PM is not equal to PT, PM is greater than PT, so PT plus the extra power loss is due to ammeter, so that is IL square into RA. All right. So in both the methods, you are going to get PM greater than PT. So this is error. This is error. If you want to minimize this error, you have to use low resistive loads. If you want to minimize this error, you have to use low resistive load in for AV method and high resistive load for VA method. VA method is useful for high resistive loads, and AV method should be useful for low resistive loads. So this way, and right. So this is a thing. And always the load side instrument is going to give the error, so that point also you should remember. All right, now here there is one more point. At what value of load resistance both the errors are going to be equal? At what value of load resistance, both the errors are going to be equal. So this error in AV method, error in VA method are equal. Here I am equating VL square by, this is RV, not RA, I am sorry, RV is equal to IL square into RA. If you solve, you will get it as geometric mean of RA and RV. They'll give you some test resistance. They'll ask you which method is better, to measure the test resistance, whether AV method is better or VA method is better. So this will decide. If the given value is, you assume, I'm telling you here. Let us assume I have got RL is equal to 100 ohms. This is the threshold point, I can say. So at this point, both the methods will give the errors as same. They'll be giving you ammeter resistance, they'll be giving you voltmeter resistance, and they'll ask you to calculate which method is better. Right. So choose like this. If the test resistance is greater than 100, go for VA method. If the test resistance is less than 100, go for AV method. That's it. Okay. So this point you need to remember. Clear? Now I have got a question. Can you tell me? Can you tell me the answer for this one? Look at the question and tell me. The power in a resistor R is estimated by measuring the voltage and current using voltmeter ammeter method. Two different arrangements can be made, arrangement can be used as shown in the circuit 1 and circuit 2. Less erroneous results are obtained by adopting. Can you tell me in which method you will get less error? Yes, given just now we have seen circuit 1, circuit 2. Circuit 1 is AV method. AV method is for what? AV method is for what? Just now I said. So remember, if you forget, ammeter internal resistance is low. So you can use it for low resistive loads. Voltmeter internal resistance is high. You can use this for high resistive loads. You remember in that way. Okay. Circuit 1 for low value of R, circuit 2 for high values of R. So only A is matching, so A is the answer. Very good, Anu. Others also respond, my dear. Others also respond. So those are some questions. That is one question on AV method and VA method. All right. So let me move on to the wattmeter section. That is measurement of power. That is AC power. Okay. We have got formulas in single phase power measurement. You'll be having only one wattmeter. The point you need to remember is here. If you are expecting the deflection torque, that means what? Measured power. Actually, true power is this one: VRMS, IRMS, cos phi. This is the true power. To measure this true power, we are going to place a meter, that is a wattmeter. So that has to indicate, PM should indicate PT. But it will never happen. So what it is going to do, it will give you some other different values. So this is possible. PM is approximately equals to PT. This is possible only when pressure coil resistance, only when XPC, that I am saying that only when pressure coil reactance is 0. So measured power is equals to true power. That is possible when you assume the pressure coil inductive reactance as equal to 0. So this is not possible actually. It's not possible. Okay. So in this case, simply the wattmeter reading is voltage across a pressure coil into current flowing through current coil into cos of angle between voltage across pressure coil and current flowing through current coil. So there is a formula. Right. Now XPC will be definitely not 0. XPC is not equal to 0. If XPC is not equal to 0, definitely PM is not equals to PT. PM is not equal to PT. You are going to get measured power greater than true power for lagging loads, measured power less than true power for leading loads. All right. So you might be, if you want me to represent, TD is directly proportional to cos phi minus beta. Beta is the impedance angle, pressure coil impedance angle. And here deflection torque is proportional to cos phi plus beta. Beta is the pressure coil impedance angle. Okay, right. Now definitely PM is not equal to PT. So as PM is not equal to PT, you will get an error. You'll get an error. So the percentage error is equals to PM by PT minus 1 or PM minus PT by PT into 100. So if you take up this, if you substitute the values measured power and true power, you are going to get plus or minus tan phi tan beta. Tan phi tan beta into 100. So this is one more important formula you need to remember. Plus is for, obviously you are going to get positive error when PM is greater. So plus is for lagging and minus is for leading power factors. So this one you need to remember. How do you calculate beta? Pressure coil impedance angle. Pressure coil impedance angle, you can calculate beta. This is pressure coil impedance angle. Pressure coil impedance angle you can calculate from pressure coil resistance, pressure coil reactance, and pressure coil impedance. This is pressure coil impedance. This is beta. So cos beta is equal to RPC by ZPC. Tan beta is equal to XPC by RPC. Tan beta is equal to XPC by RPC. So these points you need to remember. All right. Here to eliminate this error is because of pressure coil reactance. Now to eliminate this error, we will be placing capacitor. Same as like in the voltmeter multiplier, in the voltmeter range extension multiplier we are going to use now. We are going to place capacitor. So same here also. So the capacitor value here also going to be the same. Here also it's going to be same. So these are the points you need to remember. That is for single phase power measurement. And for three-phase power measurement, the only two points you need to remember is wattmeter readings. 2 wattmeter method. For 2 wattmeter method, you need to measure. You need to remember. If the reference phase is B, if the reference is B phase, and three phase three wire connection, maybe star connection, delta connection, doesn't matter. If the reference phase is B, 3 phase 3 wire, and the load is lagging load, then the wattmeter readings will be W1 is equal to VL IL cos 30 minus 5. W2 is equals to VL IL cos 30 plus 5. Now here I wanted to say, most of the times they'll give you generally. They'll not mention any reference is taken as B phase, reference is taken as R phase. They'll not mention most of the times. If they mention, be careful. Instead of B phase, if the reference phase is taken as, instead of reference phase means what? The wattmeter pressure coil terminals, finishing terminals are connected to the another phase. Out of 3 phases, in one phase 1 wattmeter will be there. In another phase 1 wattmeter will be there. Another phase, maybe R phase, Y phase, I kept 2 wattmeters, and B phase is taken as reference. So through this reference path, pressure coil finishing terminals are connected. Okay. Now if the phase is changed, if the reference phase is changed, the wattmeters will change. If the load nature is going to be changed, these wattmeters is going to be ulta, reverse. That's it. If any one are going to be changed, these wattmeter readings are going to be changed. If both are going to be changed, no change. So keep this point in mind. I'm repeating once again. If Either reference phase is going to be changed, or load nature is going to be changed. Definitely these wattmeter readings will be reverse. W1 will be, you will get it as 30 plus 5. W2 will be 30 minus 5. Okay. If both are reversed, that is reference phase reversed and load nature is also changed, then these wattmeter readings will be as usual. So based on this only, they'll be asking you the questions like at what power factor both the wattmeters will read equal, at what power factor both wattmeters will read equal and opposite, at what power factor one of the wattmeter reading will be 0. This kind of questions you can expect. Simply substitute 5 here, power factor angle. Substitute 5 equal to 0, substitute 5 equal to 30, substitute 5 equal to 60 and observe the readings. You'll get to know, you'll come to know. Okay. So these are the points you need to understand. So this is all about three-phase power by 2 wattmeter method. When you add these 2 wattmeters, readings, W1 plus W2 will give you active power, 3-phase active power, no doubt at all. When you subtract this one, that will not give you reactive power. When you subtract the 2 wattmeters, the resultant quantity is not going to be reactive power. You have to multiply with root 3. Then only that is reactive power. Now you know Q and P, then you can calculate S. So S equal to P square plus Q square. You can calculate power factor also. So cos phi is equals to cos phi is equal to what? Once you know PQ, you can calculate easily cos phi, right? This is active power and this is reactive power and this is apparent power. So this is my phi. So cos phi is P by S simply. Cos phi is adjacent by hypotenuse now, P by S. Or otherwise, there is another way also. Like you need to calculate tan inverse of Q by P. Tan inverse of Q by P. This is also fine. What is Q? Root 3 times W1 minus W2. What is P? W1 plus W2. You substitute here, you will get the tan inverse, and cos of that you will get the cos phi. So the question may be on this one, the question may be on 2 wattmeter readings, the question may be on, simply they'll be asking addition and subtraction, they'll be asking powers also. Okay. So this is 2 wattmeter method. And remember one point here, 2 wattmeter method, if you add the wattmeter readings, you are getting active power. If you subtract and multiply with root 3, you are getting reactive power. But to measure the reactive power, in 3-phase 3-wire system, 2 wattmeters are not needed. 1 wattmeter is enough. 1 wattmeter is enough. That is, connect the current coil in one phase and connect the pressure coil in another 2 phases. 1 wattmeter can measure reactive power. If they ask you question, how many wattmeters are required in 3-phase 3-wire system to measure the reactive power? 1 wattmeter is sufficient. How many wattmeters are required to measure the active power in 3-phase 3-wire system? 2 wattmeters you require. Whether it is balanced or unbalanced doesn't matter, you require 3. There is a dabba also. I think let me show you the dabba also. Let me hide and you will be getting this one. System is balanced and unbalanced. 3-phase 3-wire, 3-phase 4-wire. 4-wire means 4th wire is neutral. Whether the system is balanced or unbalanced, to measure the active power, these are the number of wattmeters required to measure the active power. 2 here, 2 here. 3-phase 4-wire balanced system. It is enough. 1 is enough. But very rarely, sometimes they'll give you 3 also. So you can go for 3. And unbalanced, definitely you require 3. Okay. So these points you need to remember. Okay. Is that clear? Or tell me, if anything, like if you feel something to be discussed in between. I'm taking the very important formulas and I'm putting them. So I've got a question here. Can you tell me the answer for this one? An LPF wattmeter of power factor 0.2 is having three voltage settings of 300, 150 and 75 volts. The two current settings of 5 amperes and 10 amperes is given. The full scale reading is 300 watts. Yeah. If the wattmeter is used with the 75 volts voltage setting and 5 amperes current setting, the multiplication factor of wattmeter is. Can you tell me what is the multiplication factor? Voltage setting into current setting into power factor divided by full scale reading. At what voltage setting I am using the wattmeter? I am using the wattmeter at 75 volt setting. Current is of 5 amperes. Power factor he has given as 0.2. Full scale reading he has given as 300. So 5 into 0.21, 75 divided by 300. So 75 divided by 150 is 2. So 75 divided by 300 is 1 by 4. So I am getting around 0.25. This is my multiplication factor. Did you get the same answer, everybody? Everybody has got the same answer or any different answers are there? Come on, my dear. People are not responding, only observing. Tell me your answer for this one. In three-phase power measurement by 2 wattmeter method, both the wattmeters had identical readings. The power factor of the load was. When it is possible, you are expecting to get same readings. The only thing you need to, if you forget the dabba, big conclusions dabba will be there. If you forget that, you remember only this wattmeter readings. VLIL cos 30 minus 5. W2 is equals to VLIL cos 30 minus 5. 30 plus 5. Now he is expecting both the wattmeter readings as equal. When it is possible, when you make phi is equal to 0, this will be cos 30, this will be cos 30. Cos 30 will be root 3 by 2. So W1 you are going to get root 3 by 2 times VLIL. W2 is also going to be root 3 by 2 times VLIL. So both the wattmeter readings are same. Both the wattmeters are readings are same at 0 power factor angle. Cos 0 unity. Very good. Very good, Yogananda and Anu. So those are some questions on wattmeter power measurement, and right. So let's enter into energy meter. I said in the single phase power, that is especially when you wanted to design a wattmeter, pressure coil should be pure resistive nature. If pressure coil, that means what, pressure coil inductive reactance should be 0. Then wattmeter will indicate true power. Otherwise, definitely apart from true value. You have to go for again compensation and all those things. Okay. Now here energy meter, it's quite reverse. The only difference between wattmeter and energy meter is you will be having a resistor bank. That's it, revolving disc. Okay. So for the shaft, whatever the disc which is revolving, for the shaft at the top and bottom, if you place springs, the disc will not rotate. Disc will move and stops. Energy meter will become wattmeter. If you add springs at the top and bottom of the spindle, energy meter will not revolve. That's it. It will not rotate because springs are going to stop, and that will become wattmeter, no doubt at all. Okay. So that's all about energy meter. Let me write the formulas. So here energy is equal to power into time, right? So we will be taking the help of resistor bank to to add up all the power consumption, whatever the energy consumption which is going to be happened. So it is a resistor bank. It is like integrating all the values, summing all the values. So that's the reason why in energy meter is called as integrating meters or integrating type. So far we have discussed PMMC, MI instrument, EMMC instrument, that is electrodynamometer type wattmeter. All are indicating meters. They have pointer. They have pointer and scale, but this does not have any pointer and scale. Energy meter. Okay, integrating type. Alright. So the energy indication we represent, it is proportional to number of revolutions. Energy indication or energy consumption is proportional to number of revolutions. So we write this one as K into P into T. Proportionality constant I am replacing. So K is the meter constant. This is very important formula. On this you can expect a question. So if you write K is equal to N divided by P into T. N units are revolutions and P units are kilowatts and time units are hours. So meter constant units are revolutions per kilowatt hour. Okay, this is one important formula you need to remember. And similarly here also, even energy meter also will give you the errors. Even every meter, if you design any meter, that will definitely give an error. There is no doubt in saying that. Okay. So here also the percentage error is going to be sine of delta minus phi divided by cos phi minus 1 into 100. Here delta is the angle between the load voltage and pressure coil current. Delta is the angle between load voltage and pressure coil current. If you remember, this is how it looks like. If the pressure coil current is perpendicular, then sine 90 minus phi. What is sine 90 minus phi? If delta equals to 90, then error will be 0. Sine 90 minus phi is cos phi. Cos phi divided by cos phi, 1. 1 minus 1 is 0. Getting delta equal to 90 means you are designing the pressure coil. You are designing the shunt magnet with pure inductive nature. That is highly impossible. So here the shunt current, if the shunt current is perpendicular, that is delta equal to 90, then you'll get error as 0. In wattmeter, pressure coil should be purely resistive. In energy meter, pressure coil or otherwise shunt magnet should be purely inductive. So designing completely pure inductive, completely resistive is not possible. So there some reactance will be there, here some resistance will be there. Due to resistance in the shunt magnet, we will not get ISH here. We will get ISH here. Therefore, delta will not be 90. Delta will be approximately near to 90. So in order to bring this one, we will add some lagging coils and all those things, right? So this is the error. This is the error due to shunt magnet resistance. Tan phi tan beta in the wattmeter plus or minus tan phi tan beta into 100. That is error due to pressure coil reactance, and here the error is due to shunt magnet resistance. Okay, there pressure coil should be purely resistive. Here pressure coil should be purely inductive. Otherwise, you will not get error. Then only you will not get error. Otherwise, you will get error. So this is the formula. This is one formula you need to remember, and this is one formula you need to remember when it comes to energy meter. Okay. So I have got one question, very good question. Please try this one. Hi, Sai Kumar. How are you? The disk of an energy meter makes 600 revolutions per unit energy consumption. Unit energy consumption means 1 kilowatt hour. Unit means per unit energy consumption. Okay. 1 unit means 1 kilowatt hour. When a load of 1 kilowatt is connected, the disk rotates at 10.2 rpm. If the load is connected for 12 hours, how many units are recorded as error? How many units are recorded as error? So let me first of all put the information in terms of data. Let me put them in terms of the quantities. The disk of an energy meter makes 600 revolutions per unit energy consumption. That means what 600 revolutions means? 600 revolutions per unit energy consumption. That means what? Kilowatt hour. Revolutions per kilowatt hour. This is the value of K. There is a value of K. So K he has given as 600. Now we know the load as 1 kilowatt, and we are operating that load for 12 hours. So when load is connected, the number of revolutions are 10.2 rpm. Revolutions per minute. If the load is connected for 12 hours, how many units are recorded as error? Okay. First of all, what is the true energy consumption? Let's see. What is the true energy consumption? Let's see. I have a load. The load is of 1 kilowatt. Okay, this is my power. What is the true power? Time, let me take up this as 1 hour. So the true energy consumption will be 1 kilowatt hour. This is the true energy consumption per 1 hour. Now to measure this energy consumption, to measure this energy, I am placing a meter. To measure this energy, I am placing a meter. Let me show you the meter. This is my energy meter. This energy meter has to indicate this one. Let's check now. This energy meter has a meter constant of K is equals to 600 revolutions per kilowatt hour. Okay, 600 revolutions per kilowatt hour. That means what? K is equal to N divided by EM. K is equal to N divided by PT, na? So that PT, P into time is nothing but measured energy. So I have to calculate this measured energy. So measured energy will be 10.2 revolutions per minute. But I need revolutions. Into 60, you are going to get revolutions. 10.2 into 60 divided by K. K is 600. So if you do so, then probably this will be 60, 10. So you will be getting it as around 1.02 kilowatt hours. This is the energy recorded by the meter. Consumption is only 1 kilowatt hour, but recorded by the meter is recording more than the actual value. So definitely error will be there. How much error? Now the error is measured value minus true value 1.02 minus 1. So you are going to get it as 0.02 kilowatt hours. 0.02 kilowatt hours for only 1 hour, but he is operating the load for 12 hours. So 0.02 into 12. So you will be getting it as 0.24 kilowatt hours. Option A is readily available. Absolutely wrong answer. Option A is absolutely wrong answer. Okay. Is that clear for everyone? Valvekar, I'll tell you one mail ID. You can mail to that. Support at BYJU'S That is a mail ID. If that is not, if you did not get any response, you just mail to me. We'll look into it. My mail ID is this one, Naveen Gollapally @gradeup.com. Just mail to this stating that you have that kind of rule number, test series rule number, no, any kind of any identity. Just tell that. Send it by stating your identity. I'll forward it to the concerned person. Okay. Sorry for the inconvenience. All right. Now let's move on to the another question. I have this question. The braking torque provided by a permanent magnet in a single phase energy meter is proportional to the square of the flux of the permanent magnet, speed of the meter, distance of the permanent magnet from the center of the disk, and all of the above. So braking torque when you in the permanent magnet, if you place the disk, that disk will cut the permanent magnet. So whenever the disk is cutting the permanent magnetic field, you will get an induced EMF, you will get a torque, right? All right. So braking torque also. So I can write the torque is proportional to flux into current, same as like motor. Energy meter is also same like a motor, right? The torque is not only depending upon flux and current, but also depends upon the radius of the disk. So I can put it as radius. This is the radius of the disk. Okay. So let me write this as braking torque is equals to This is armature current. I am not writing it as armature current. This is a disk current. Disk current now. So some constant K into phi into disk current can be written as disk EMF divided by disk resistance. Disk EMF divided by disk resistance. Small r I am taking. This is disk resistance. Now we know EMF. EMF is E is equal to K phi omega, na? K phi omega. You can write it as K into phi into N. Omega anyhow that is 2 pi by 60. Let's make it as constant. So I am not writing again K. So simply I am mentioning it as K into phi into this is phi omega, or otherwise phi N by R into R. So if you do so, breaking torque is proportional to square of the permanent magnet, rotation of the disk, revolution of the disk, and this is radius of the disk, or also you can replace the distance between the center of the disk and the permanent magnet. You can also replace R with D divided by R, inversely proportional to resistance of the disk. So all are correct. All are correct. Very good, Sai Kumar. Okay. Now can you tell me what is the answer for this one? Pressure coil of an induction type energy meter. Wattmeter pressure coil, how to design? Wattmeter pressure coil should be highly resistive. Purely resistive is not possible, so should be highly resistive. Pressure coil of the energy meter is ulta. The ulta means not low resistive, it is highly inductive. It should be highly inductive. Not purely inductive, not purely resistive. It's not possible. It's not possible. So there is a very lengthy question, and don't get afraid by looking at this question because this question is very simple question. If you can understand, it's very simple. Look at this one. The two pressure coils of a single phase dynamometer type power factor meter are connected as follows. One coil is connected in series with the non-inductive resistance, and the other coil is connected in parallel with the inductive choke coil. And one coil is connected in series with the inductive resistance, and other coil is connected in series with the inductive choke coil. So this is how they have given. If you remember the construction, that's fine. If you remember the construction of power factor wattmeter, you can easily answer that. Okay, let me show you that. Here itself I'm drawing. The current coil will be as usual, same as wattmeter, energy meter, power factor meter construction. Not too much difficult. There's a small differences are there. That's it. So this is a current coil. You can place in series with a load. And now the pressure coil is made into two parts. So one is going to be, this coil is going to be series. This coil is connected in series with a pure resistance. Okay. And another coil is going to be connected like this in series with pure inductance. Okay, and these coils are connected 90 degrees apart from each other, physically 90 degrees apart from each other. This is a moving coil, pressure coil only, same like pressure coil only. So it's a moving coil. Okay, you don't require any controlling torque here, because the resistance nature coil and inductance nature coil itself is going to damp the oscillations, and you don't need a control torque at all, to say exactly. So one coil connected in series with the non-inductive resistance. So one coil is connected in series with the non-inductive resistance. Another coil is connected in series with the choke coil, or otherwise inductance nature. By the way, the coils are connected in 90 degrees manner. Okay, 90 degrees with respect to each other. Okay, so this point you need to remember. So the moment, the pointer deflection, the deflection itself power factor. So theta itself power factor. So we will design like that. So these are some questions on watt meter, energy meter, PMMC, MI, and um, power factor. And let's have a bridges. Let's look into the bridges. I have bridge. There are so many bridges, you know. The only thing you need to remember, whether it is going to be DC bridge, whether it is going to be AC bridge, the only thing you need to remember is opposite arm product must be equal. Okay, this is going to be P, Q, R, or let me mention this one as Z1, Z2, Z1, Z2, Z3, Z4. Maybe AC supply or DC supply. You are going to give the detector. Okay. For DC supply, you will be having only resistances Z equal to R. Okay. And detector is tangent galvanometer. Tangent galvanometer. Okay. For AC supply, and balanced condition is same for anything. Balanced condition is same for anything, that is opposite arm products must be equal. So that is Z1, Z4 is equal to Z2, Z3. And here in the four arms, out of any one can be unknown. There is no such kind of a rule like that, place Z1 as unknown. Okay, not like that. It can be anywhere. Maybe Z1 can be unknown, Z2 can be unknown, Z3 can be unknown, right? Any one should be unknown, remaining three should be known values. So they will give you, they'll ask you to calculate Z4, they'll ask you to calculate Z3. So it depends. So balanced condition. Z1, Z4 is equals to Z2, Z3. For DC only magnitude. For AC, phase angle also should be balanced. That is theta 1 plus theta 4 is equal to theta 2 plus theta 3. Okay. Now, here I wanted to say one more thing. For AC supply, the detectors up to 125 hertz or 150 hertz, you can go ahead for up to 100 hertz or 125 hertz, up to 100 hertz. You can go ahead with the vibration galvanometer. 50 to 100 hertz, that is fine. Vibration galvanometer. Greater than 100 hertz, that is greater than 125 hertz to 1 kilohertz, you can go for headphones. And greater than 3 kilohertz to 10 kilohertz, you can go for tuned amplifiers. When you tune, you can hear a noise or a sound. Tunable amplifiers. So these are the detector we use to find the noise, or otherwise to get to find out the balanced condition. Now there are so many bridges, like, you know, to measure the resistance, what are the bridges? To measure the inductance, what are the bridges? To measure the capacitance, what are the bridges? Let me tell you one thing. You just go through my Telegram channel. I have pinned in my Telegram channel. You can search at the end. I have got Telegram channel link also. I have pinned the formula sheet. I have pinned all electrical measurement formulas. Right now, they have, whatever I have discussed that formulas I have represented. Okay, including bridges also. Bridge figure and bridge balancing condition, the formula, the values also, unknown branch values also I have mentioned. I have pinned it. So electrical measurements, I have pinned. So you can go through my Telegram channel, check the pinned one. The name is Electrical Measurements Formula Sheet. Electrical measurements formula sheet or formulas. That's it. Yeah, can you tell me what is the answer here? Can you tell me what is the answer here? The Wheatstone bridge method of resistance measurement is ideally suitable for measurement of resistance values in the range of. Ideally suitable for the measurement of resistance in the range of. Wheatstone bridge, it's a Wheatstone bridge. Wheatstone bridge for medium resistance measurement. Kelvin's bridge for low resistance measurement. Okay. Even Carey-Foster bridge also medium resistance. Okay. Yeah, medium resistance is obviously greater than 1. Greater than 1, not this one, not this one, not this one. So this is the thing. So for this one, you can go ahead with the Kelvin's double bridge. For this one, you can go ahead with the loss of charge method or Megger. So Wheatstone bridge, you can go ahead 100 ohms to 10 kilo ohms. The range is less than 1 ohm is Kelvin's double bridge. 1 ohm to 100 kilo is medium resistance. Greater than 100 kilo is greater than 100 kilo. This is 100 kilo ohm, 100 kilo ohms to mega ohms. Greater than 100 kilo ohms is large resistance. SST, it is actually electrical by Naveen Gollapally. You can search it like that. Electrical by Naveen underscore Gollapally. You'll get it. Now, can you calculate the answer for this one? Question is so lengthy, but answer is so simple. 4 arms of AC bridge are arranged as follows to obtain the balance. So, arm PQ, arm QR like that. So, you mention, take up. This is P and this is Q and the resistance is of 250 ohms. QR is of 500. So, Q to R I have got 500. SP is 0.2. So, between P and S I have got 0.2 microfarad capacitor. And arm SR is unknown. So what is this impedance? A source of 200 volts 1 kilohertz is applied between terminal P and R. So terminal P and R I am applying a source of 200 volts and 1 kilohertz. Let me hide so that you can see 200 volts and 1 kilohertz. The value of unknown parameter arm is, it's like, resistor, this is resistor and this is resistor. So obviously you have to get a capacitor here. It looks like a DSAT bridge. It looks like a DSAT bridge. So obviously it should be a capacitor. Out of 4 options, definitely one option should be capacitor. All 4 options are capacitor, then you have to calculate. There is no other way. Okay. Now, tell me, can you tell me how do you calculate? Opposite arm products equal to? Opposite arm products must be equal, na? Opposite arm impedances product must be equal. So Z into 250 is equal to 0.2 micro into 500. So that is 500 into 0.2 micro. I can take it as 1 by j omega c. Omega is 2 pi f, na? 2 pi f. Omega is equal to 2 pi f. F is 1000. So it will be 2000 pi. So I can write it as 2000 pi into C. What is C? 0.2 micro. If this micro goes up, that will be 10 to the power of 6. Now I can cancel out here. 250 2's. You can solve this one, so you'll get a Z. Probably you'll get Z as, I think, 0.1. So if you solve this one, probably you'll get a Z as 0.1. So once you will get the Z value, you will get the Z value, how much? Something 10 to the power of 6, 2000.2. So 2000, if it goes up 1000 divided by 0.2 is around something value you will get here. Some minus J, some ohms will be there. So you have to check whether zero point 0.1 microfarad is satisfying or 0.2 microfarad is satisfying. You have to check. So 1 by J 2000 pi into 0.1 micro. So whether this value is equal to this value or not, you have to check. So that is the thing you need to cross check. Vishwadis is asking medium resistance. Wheatstone bridge is going to measure medium resistance, and how it is going to measure 100 ohms to 10 kilo ohms. So 10 kilo ohms is not going to be. Do you think that 10 kilo ohms is a large value? That is about the reason I said the range of the resistance also. Low resistance is classified as less than 1 ohm. Medium resistance is classified as 1 ohm to 100 kilo ohms. Up to 100 kilo ohms is medium resistance only. So high resistance is greater than 100 kilo ohms. So this is the thing, right? Similarly, I've got one more question. Is that okay? I forgot your name. Vishwadit, is that okay? Right. You can check this one. I think options are not visible, but anyhow, let me hide so that you can see. The current transformer never be operated on open circuit for which of the following? For which of the following? The core flux will increase enormously. The eddy current and hysteresis loss will increase to a large value. A very low voltage will be induced in the multi-turn secondary. Eddy current and hysteresis loss will decrease to a large value. So which is the correct answer, my dear? What could be the correct answer? Come on, my dear, respond. So it is a current transformer. Generally, current transformer primary is going to be less turns, whereas secondary is going to be of huge turns. So do not open this one. If you open this one, what happens? This is the primary current is in the range of large value, that is 1 kiloampere, 2 kiloamperes, right? So when such large value of current is flowing, definitely large value of flux is going to be produced from the primary side. Let it be number of turns, 1 or 2, doesn't matter. Number of turns into current, very huge current is going to produce very huge MMF. That huge MMF definitely creates a huge amount of EMF in the secondary side. When you open circuit this one, a large value of voltage is going to be induced and that will be damaged. It is not low voltage, it is a large voltage. Eddy current and hysteresis loss will not decrease, it will actually increase. Why? Because of huge flux. Because of huge flux. When you open this one, secondary side current is 0. As secondary side current is 0, the opposite component of flux is 0. So secondary current is 0, so secondary flux is 0. As secondary flux is 0, secondary flux phi 2 cannot oppose phi 1 because phi 2 is 0. If this is closed or short circuited, there will be secondary current circulation. That current circulation will produce a flux, and that flux and primary flux will be compensated, and the flux in the core will be maintained as minimum value. But if secondary is open circuited, it leads to very huge value of flux, and the core also goes to deep saturation. And because of very huge flux, eddy current loss and hysteresis loss will definitely increase, no doubt at all. So 1 and 2 are correct. One and two are correct. Very good, Vishwadit and Yashasri. Right. So it's this is all about CRO. I have some formulas. Sometimes I'll ask you the formulas here. Velocity of electron is fine. 2q into EA divided by m. Q is the charge of electron. M is the mass of electron. 1.602 into 10 to the power of minus 19, and mass is going to be 9.11 into 10 to the power of minus 31 kgs. And EA is the accelerating anode voltage. Accelerating anode voltage. All right. So the question here is sometimes they'll very rare, it's very rare to ask the velocity of the electron. This is the velocity of the beam or velocity of beam or electron. They'll ask you deflection sensitivity of the CRO, deflection factor of the CRO. So deflection sensitivity is equals to d by ed, that is capital L into small ld divided by 2 into ea into small d. So capital L is the distance between the screen and the center of the deflection plates. So I cannot write all those things here. Small ld is the length of the deflection plates. EA is the accelerating plate voltages. D is the distance between the plates, deflecting plates. Okay. So you are going to get this as mm per volt. Very, very small distance. Deflection sensitivity. This is deflection sensitivity. Deflection factor will be ulta, reverse, reciprocal of deflection sensitivity. So deflection factor is 1 by SD, that is ED by D. Alright. So this units will be volt per mm. So these two formulas you need to remember when it comes to CRO. Okay, based on this one, they'll ask you. They'll give you length of the deflection plates like that. They'll ask you to calculate the deflection factor or deflection sensitivity. If not this, the question will be on this one. Phase measurement and frequency measurement. Phase measurement and frequency measurement. Phase measurement is like this. When the angle between the two inputs is 0 degrees, what will be the image on the screen? When the angle between the two inputs is 90 degrees, what will be the image on the screen? When the angle between two inputs is 180 degrees, what will be the image on the screen? Similarly, when the angle is 270 degrees, what will be the image on the screen? So this kind of questions will ask you. When the angle between two input signals is 0, it will be a straight line, but with respect to x-axis, it will be 45 degrees. When the angle is 90, it will be a circle in the clockwise. When the angle is 180, it will be again a straight line. You can say it as diagonal line to say exactly, but at an angle of 135 degrees. When angle is 270, it will be anti-clockwise, circle again. Now between 0 to 90, between 90 to 180 and 180 to 270, 270 to 360, it is going to be like this. It is going to be an ellipse. It is going to be an ellipse. And everywhere you can write the phi. Here it is going to be phi. Let me write it as phi 1. Phi 1 is going to be sine inverse of y intersection point divided by y maximum. No issues. You can write x intersection point divided by x maximum also. Okay. Then phi 2 you will get it as 90 plus phi 1. 90 plus phi 1, sine inverse of y intersection by y maximum. That phi 1 you cannot write. You should not write same formula I am saying. 90 plus. Here phi 3 in this third quadrant it will be 180 plus. In the fourth quadrant you can write it as minus sine inverse. You can write. Okay. So 0 degrees you are going to get a straight line. A is Q. 150 degrees is an ellipse R. 90 degrees is a circle P. So P R, the QRP. QRP. Option A is the answer. Nobody is answering. Okay, options are not visible. Huh? Options are not visible. All right. Anyhow, so this is a phase measurement. There will be question on frequency measurement also. I forget that one. Frequency measurement, Fy by Fx is equals to Nx by Ny. Horizontal cut method, touch method. Number of cuts in horizontal. Number of horizontal cuts and number of vertical cuts. Cut method is the best thing. Instead of going for touch method, cut method is best thing. Number of horizontal cuts. So they'll ask you to calculate Fy or otherwise Fx by giving and frequencies and the image. Let's adjust pattern image. Okay. It's like let me take up one example here. I have an image like this. Okay. Okay. So if I have an image like this, you can better to go for cut method. So cut in horizontal manner, cut in vertical manner. So vertical cuts are ny is equal to 2. Horizontal cuts 1, 2, 3. Nx is equal to 3. So Fy by Fx ratio, the frequency ratio is 3 by 2. They'll ask you what is the vertical input frequency. They'll give you Fx frequency, that is horizontal input frequency. So Fy is equal to 3 by 2 times Fx. So in that way, you can expect. Now here when it comes to the last one is errors. Error simply is nothing but deviation. Measured value minus true value. No need to be only AM minus AT. It can be true value minus AM also. No issues. We call this as absolute error. No issues. Okay. The percentage error we take up it as AM minus AT divided by 80 into 100. AM minus AT we can also call it as del A, del E. In some textbooks they'll write in del E like this. So we can also call this as absolute errors. This is percentage error or percentage relative error, percentage limiting error. We also call it as. Okay. So this is the only formula you need to do it. Okay. But there are some kind of models like it's like how when the resistors are connected in series, when the resistors are connected in parallel, how the tolerance value or how the limiting value is going to be existed. So that kind of questions they'll ask you. Let's see. Three resistances are rated as follows: R1, R2, R3. What will be the limiting error in ohms if these three resistors are connected in series? So when the resistors are connected in series, absolute errors, the series connection, that means what if you have, let me write here. Coming to the error, if mathematical operation is addition or subtraction, then go for add absolute errors. Add absolute errors. If mathematical calculation is multiplication, remember this point, if mathematical calculation is multiplication or division, add percentage errors. So here it is, the resistors are connected in series. Connected in series means R1 plus R2 plus R3. So it's addition. So take the absolute errors only. So he's asking what will be the limiting error. That will be the limiting error. So take the absolute errors, and he has mentioned also at all absolute errors only. 5% of 40, how much? 5% of 40, it is going to be 2 or 2, it seems. 5 4s are 20, 20 by 10, 2. So that means what? 40 plus or minus 2 ohms. This is absolute error. So I can represent it as 40 plus or minus 2 ohms now. This is the absolute error. That means what? Whenever if you design a 40 ohm resistance, there will be a deviation of 2 ohms. Maybe from 38 to 42, it will be any one value. Similarly, R2, 5% of 80. So 5% of 80, I am going to get it as 40 divided by 10, 4. Now R3, 5% of 50. So it will be 2.5. So 6.5 and plus 2. So simply add these absolute errors. So you are going to get it as 8.5. So the answer is 8.5. A is the answer. Very good, Yashasri. Viswajit, instrument transformers formula. It's very lengthy in instrument transformer formula. So this is my Telegram channel, by the way. Uh, they'll ask you formulas means phase error and ratio error formulas are very lengthy. Okay. Uh, but in instrument transformer, there are other formulas also. If you are asking about these formulas, ratios, there are ratios like what are the ratios? Yeah, transformation ratio. We represent this as with R. This is called as actual ratio, R actual ratio. For CT, how to represent is CT primary current is higher value, secondary current is lower value. CT and PT both are going to step down the values. CT is going to step down the current, PT is going to step down the voltage. Okay. So transformation ratio formula is like which current is higher? Obviously primary current. So primary current to the secondary current. Primary current to the secondary current. These are not rated currents, okay? Similarly, PT, primary voltage is large, secondary voltage is small. So always write all the ratios high to low. Whether it is CT ratios or PT ratios, you write all the ratios in high to low. Numerator is higher value, denominator is lower value. This makes the difference between the ratios of instrument transformers and power transformers. This makes a difference. PT transformation ratio is going to be high voltage will be on primary side. So primary voltage to secondary voltage. Now where there is one more ratio that is called nominal ratio. Yeah, nominal ratio. Generally it is given with Kn. Nominal values are nothing but rated values. So high value to low value again. So rated primary current to the rated secondary current. Rated primary current to the rated secondary current. Similarly, PT also rated high voltage. High voltage is on primary side. So rated primary voltage to the rated secondary voltage. Now the last one, there is one more formula, that is, what is that? Turns ratio. Generally given with N. Turns ratio also, higher turns to the lower turns. Higher turns will be on secondary. So secondary turns to primary turns. Now coming to the PT, more number of turns is on primary. More number of turns is on primary. So primary turns to secondary turns. Now there is a ratio error at last. We take up this as ratio error Kn minus R divided by R into 100. So R, there is a formula. So generally they'll not, it's a very lengthy thing. R, you will get it in terms of sine delta, cos delta, I mu ratio. And if I am able to recall this one, I'll try to do this, but no space directly. Okay. I think if you remember, I'll give a hint. Transformation ratio is going to be, it will be like this, I think. N plus IW into cos delta minus I mu into sin delta divided by I2. So in that manner, you'll be having. So phase error will be different again. Phase error will be ulta, you'll get. I mu into cos delta minus or plus IW into sin delta divided by N times I2. So that kind of formulas I have given in the list in the formula sheet. If not given, just please ping me. I'll add up that also. Okay. So these are some formulas Accessory, what kind of relative errors, what do you want? What do you want me to say? Like how we are going to calculate? If you've got any problems, like if you are stucking with that relative errors problem, please send that me. How to solve that kind of questions, I'll tell you. Okay. Vishwajit, the only thing I wanted to say at this moment is, do not uh, not get tension. That is the first thing I wanted to say. Whatever happened is happened. You have studied something, so just recall them. If you made any short notes, like if you make any formula things, if you make any formulas, uh, try to recall them. That is fine. So nothing new to be added again. That is my sincere opinion. Have a glance, that's it. Don't get into the textbooks and don't text, not only textbooks, any kind of, if your notes also, do not try to open the notes also. If you have any like short notes, like a simple paper like that, try to have a glance on that one. That's it. Relative limiting error with respect to full scale deflection. Okay, it is like this, SSRE, I'll tell you. Let me add a page so that I can do something. Just give me a minute, I'm adding. Right. I have a question, just generally I'm example I'm taking. A 0 to 100 watts watt meter. 0 to 100 watts watt meter has guaranteed accuracy error of plus or minus 1% of full scale value or full scale reading they'll give you. So that means what he wanted to convey that I have designed a 100 watts range watt meter. In that plus or minus 1% full scale deflection, definitely error will be there. Whatever the value you measure, whether you measure 10 watts, whether you measure 20 watts, whether you measure 50, 100, 90, anything you measure, definitely 1% error will be there. Now, then the percentage error or percentage limiting error while measuring, 75 watts or otherwise 80 watts. Let me take up 80 watts. While measuring 80 watts is, if you're feeling uncomfortable with watt, you can take up with volt also, no issues. So this is my voltmeter range. In that range, I can measure 0 to 100, any value I can measure. You measure any value, 1% deflection error will be there. That is why he said that as guaranteed, definitely there will be an error. So this 1% of full scale value is this 100. So plus or minus 1% of full scale is 1% into 100, you are going to get it as plus or minus 1. So this plus or minus 1 volt, definitely deviation will be there. Whether you apply 10 volts, 20 volts, 25, doesn't matter. If you apply 10 volts, 10 plus or minus 1, the answer will not be 10 volts. It will be from minus 9 to 10, minus 9 to 11, any value it can be. So this is an absolute error, definitely you are going to get. An absolute error, for the sure you are going to get. Now, I am applying 80 volts to the voltmeter. If I apply 80 volts to the voltmeter, how much value it is going to be indicated? So this is my true value. This is the true value I am going to apply. Now, how much value it is going to be indicated? So obviously, your percentage limiting error is equals to del A, that is absolute error divided by true value into 100. Okay. So I know the true value, I know the del A. So del A is of plus or minus 1, true value is 80 into 100. So let me take up this one, 10 by 8 percent plus or minus 10 by 8%. So this is the percentage limiting error. Very rarely they'll give you the guaranteed accuracy error of plus or minus 1% of reading, not full scale value. Very rarely they'll ask you of 1% of plus or minus 1% of reading. Then at that time you have to take this as not 100, not 100. You have to take it as 80. So with that you have to go ahead. Okay. Is this clear now? I think it is not. Is it? I think it is clear. Yeah, irrespective of the voltage you apply, whether you apply 10, chalo. If that means what, here I am applying 80 na, I am applying 80, so definitely I am going to get the range from 79 to 81. This is the limit. There is a range. If I apply 10, my value will be 9 to 11. If I apply 20, my value will be 19 to 21. In that range you are going to get. Obviously higher value is not possible. So 19 to 20, in between 19 to 20 you can get the answer. Okay, chalo. Thank you. So that's all about the electrical measurement section. And if you, this is my Telegram channel, you can go here and you can download the formula sheet. Electrical measurements form. You just go to the pinned one. Pinned messages are there. Electrical measurements formula sheet you can download. Okay, that will definitely help you. All right. Thank you. Thank you so much. Have a nice day. Bye bye. See you. Prem, actually, this is for the BARC examination, not from basics. I just give a formula, some important points, and some formulas and formula based questions. That's it. Okay. All right. Chalo then. See you then. Any other questions if you have? Anybody? Any other questions? Okay then. Thank you. Thank you so much. Have a nice day. If you have any questions, please take a snapshot, and if you can post me on Telegram channel, or you can directly reach me on Telegram. Okay. Thank you. Thank you so much. Have a nice day. Bye bye. See you. All the best.